Hey, let's jump back into it. We just did this example with the 72-inch ladder against the house. Before we go any further, I want to pause for a moment and think about just the procedure on how to tackle these related rates problems. Now, the truth is, every one of these is different and requires different thinking, and there's some creativity to just exactly how you go about them. But generally speaking, there are kind of some steps that we can follow that I hope will really make things a lot easier as we look at these related rates problems. Okay, so let's see here. Step number one, when we do a related rates problem, make a drawing. So that's what we did here in this ladder problem. We drew the house, we drew the ladder. Even part of making the drawing is labeling the different parts of the drawing correctly as either a constant, if it's not changing, or as a variable, if it is changing, if that particular thing that's being labeled is in motion. So when we drew our ladder, right, we labeled the ladder itself as 72 inches because that's not changing, but the distances along the sides of the house are changing. So we had to use variables for those. Once you have the drawing, then you're really setting yourself up to be able to execute and go through the rest of the problem. From the drawing, step number two is to find an equation relating the quantities. When I say the quantities, I'm referring to the variables that you put in the drawing. So once we had that drawing of the ladder with X and Y labeled, then we were able to look back at that and say, hey, you know what, there's a right triangle here. We know the three sides of the triangle. And so we can create an equation using the Pythagorean theorem. Sometimes what the equation will be, maybe you'll see it right away. Other times you're not going to see it right away. When it comes to getting the equation right now, all of math that you've learned before is available, and we could call upon anything at any time. In that last question, we needed the Pythagorean theorem. Other times we're going to use other formulas that we've seen before. It's not unusual to use formulas from geometry, right? Like the area of a circle, the volume of a sphere, that sort of thing could be called upon. Maybe we use trig. Somehow we connect, the three sides of a triangle with one of the trig functions. Anything's available, but generally speaking, from your drawing, come up with an equation that involves all of your variables or all of your quantities. Once you have the equation, then you're really set up to get to an answer pretty quickly after that. Take the derivative of both sides of your equation with respect to t representing time. Obviously take your time with that, right? But that's typically not as challenging as that drawing and getting that equation in the first place. Now, once you have the derivative of both sides with respect to t, then it's time to finish it off. What you would do at that point is think, okay, I've got a couple of different derivatives involved in this new equation that I have. Which one of them is the question asking about? So when we did that ladder question, at that point, once we had the derivative of both sides, we looked back up to the question itself. How fast is the top of the ladder sliding down the house? We realized, okay, that's talking about dy over dt. So that's the value I'm trying to figure out. Well, then it must be that I can plug in a value of x, a value of y, and a value of dx over dt. Once I put all those values in, then I can solve for dy over dt and get my answer. Kind of looking at these steps, the hardest steps typically are making that drawing, and then from the drawing, getting the equation relating to quantities. So take your time with the drawing. Don't rush it. Make sure it's accurate, as accurate as you can be. Make sure that you're labeling constants versus variables correctly. And then from there, to get the equation again, sometimes it might be, you might see it immediately. Other times it's going to take some thought. Those first two steps are the most challenging. And then obviously you want to execute the rest accurately too. Okay, let's get into some more examples. This is a fun one. A Ferris wheel. A Ferris wheel with a radius of 10 meters is rotating at a rate of 1 revolution every 2 minutes. Look at a couple of questions. Part A, how fast is a rider rising when he or she is 16 meters above ground level? Thinking about this Ferris wheel, this is actually a pretty big Ferris wheel, right? The radius is 10 meters. So the whole Ferris wheel is 20 meters tall. That's over 60 feet. That's a big one. Okay, so if you're familiar with the Ferris wheel, right, you get into the little car, the little bench, and then it starts to go, and you go up, and then they have to put everybody on the ride, right, slowly. So it's kind of slow at first, but then once everybody's on, then you're just kind of going around in a circle, and maybe you get a few trips all the way around before they start to unload all the cars slowly. All right. So when somebody's 16 meters up, how fast are they rising just vertically? Part B, how fast is a rider moving horizontally at the same moment? Okay, cool. Let's go to the paper. Here we go. Ferris wheel, radius 10 meters, rotating at a rate of 1 revolution every 2 minutes. How fast is a rider rising at 16 meters above ground level? So we'll follow our steps. The first step was to make a drawing. So I'm going to try and draw this Ferris wheel, right? I'm going to say this is ground level. And then the Ferris wheel is going to do something like this and come right down to ground level like so. So that's where people get on the ride. A lot of times they make Ferris wheels up on a platform. We'll just say that's ground level, whatever it is. All right. Something like that. Okay, so let's label maybe the center of the Ferris wheel. Now the person on the ride they're up above halfway, right? 16 meters. So maybe I'll put them up here, and their little car is rotating kind of up and back. All right, looks good. We start to label the different parts. Let's see. This distance here, we know our radius is 10 meters, right? That's also the distance straight down to the ground. I don't know if that will be helpful or not. Then, check. Let's make a little triangle right there, little right triangle. Connecting the center of the Ferris wheel up to where they're sitting. So here's what's happening. So as they're sitting there, right, they're going up and back. We only care about how fast they are rising vertically. So that is this distance of my triangle. Notice that is changing as they move. So I'm going to label this with a Y. In the end, I want to know what is dy over dt. How fast is that y value changing as they go up and back? Okay. Now, what else can we label here? We only have one variable. That's not going to be enough. What else did they tell us? They said the Ferris wheel is rotating at 1 revolution every 2 minutes. Because they're telling us about rotation, how fast this is spinning, we want to label this little angle here maybe as theta. Because we know how fast it's rotating, we know the rate of change of theta. So that's something we got to get involved. Okay, From this drawing, we can set up an equation. We can connect theta with y. We also know that that hypotenuse there is 10. Let's use a trig function. Which trig function would connect theta, y, and the 10? Think, well, that'd be opposite over hypotenuse. The sine of theta equals y over 10. Perfect, got it. If we wanted to make this look a little bit simpler for derivative purposes, maybe we multiply the 10 over. Let's call it 10 sine theta equals y. And we're looking good. We have an equation that's relating our two variables, y and theta. Okay, next step, take a derivative of both sides with respect to t. All right, so derivative here, well, let's see, 10 sine theta, that derivative is going to be 10 cosine theta times d theta over dt. And that's going to be equal to derivative y is simply dy over dt. Looking good. All right. Once we have our derivative equation, let's look back at the question. What were they actually asking? How fast are they rising? Well, that's dy over dt. That's what we're trying to figure out. So it must be that we know the value of theta to plug in for the moment that's in question, and we know the value of d theta over dt. Let's think about this. What moment are we looking at? It says, how fast are they rising when they're 16 meters above the ground? Well, when they're 16 meters above the ground, what does y equal? Let's start with that. Well, the way that we've drawn it, right, just that little part is y. At that moment, y would equal 6. 16 meters up. So we can use this to figure out what theta is back in our original equation. So we know sine theta equals 6 over 10. We can figure out the value of theta at that same moment. Here, theta would equal inverse sine, and let's reduce that. Let's call it 3/5. You know what? I think we're just going to leave it like that. I think if we put that in a calculator, we might get a nice answer, we might not. I'm just going to leave it like this and only round at the very end. Okay, cool. We know what theta equals at that moment. We can plug this in. How about d theta over dt? Now for that, that's telling us the rate of change of our angle with respect to time. They told us that it's 1 revolution every 2 minutes. We got to think through that. How is that going to help us with d theta over dt? 1 revolution every 2 minutes. So we're thinking of theta as in radians. How many radians is it to do 1 revolution? Now to go all the way around, that's 2 pi radians. And we'll divide that by how long it takes, 2 minutes. Notice that d theta over dt, right? Check out the units, right? The units of the theta is radians. The units of t here is minutes. So we can literally take, well, it goes through 2 pi radians in every 2 minutes. So d theta over dt, divide those, that's pi radians per minute. Right. We are all set. We can plug these in and we're going to have it. 10 cosine inverse sine 3/5 times pi equals dy over dt. Grab our calculator. let's say dy over dt equals, make sure you're in radians, 10 cos inverse sine of 3/5. Multiply that by pi, and I got 25, rounding to 2 places, I think is what we want, 25.13. Interesting, okay. What are the units on that? 25.13. Let's see. The units of y, 6, that was meters, right? 6 meters, time was 2 minutes, right? Units of y divided by units of time, meters per minute. That's kind of hard to wrap my head around, like how fast, what's their experience in the Ferris wheel, 25.13 meters per minute. What if we divided this by 60 and got meters per second? If I divide by 60, I get 0.42 meters per second. Okay, that gives me a better idea of what they're actually experiencing. A little less than half a meter every second. That's not too bad. Doesn't seem too bad. Okay. Then part B, how fast is a rider moving horizontally at the same moment? This time we'll do it for the horizontal. Let me recreate the drawing. Pretty much kind of flattened out there. Pretty much going to be the same drawing. They're still here up at 16 meters. I'm going to draw that triangle. I'm going to label this theta. But now this time we don't care about the vertical movement. We want the horizontal. So we're going to label that maybe as x for the horizontal. Again, they're kind of going back that way. So let's see, how can we connect theta and x and even the 10 here in an equation? Well, we'll use cosine of theta, adjacent over hypotenuse, x over 10, and maybe we'll say 10 cos theta equals x. Make it a little bit easier for our derivative. Right. Taking the derivative of both sides, let's do it. Derivative cosine negative sines, we got negative 10 sine theta d theta over dt equals dx over dt. Now what's great, here we're looking for dx over dt, how fast they're moving horizontally. We already know the value of theta and d theta over dt for the same moment. We can just put those right in from our work before. Theta was inverse sine 3/5. D theta over dt was pi. And we could do it. Turns out here, even like the sine of the arc sine, those cancel. And a little bit faster, we could just do negative 10 times 3/5 times pi. And here, okay, dx over dt, what are we going to get? A negative answer, negative 18.85. And that are units of x and t, that's meters per minute. Why is it negative? Well, because at that moment, x, this distance here is shrinking as that car moves back this way, right? That triangle is going to go up and to the left. Makes sense it would be negative. We'd probably ignore the negative in our answer and just say the car is moving horizontally at 18.85 meters per minute. If we wanted to know what that was in seconds, meters per second, we could divide by 60. It's 0.31 meters per second. Maybe gives us a little bit better idea again of what they're actually feeling. So they are, at that moment, they're going more up than they are back. But pretty soon that'll, work itself out. And at the very top, they'll only be moving horizontally, and then, their experience going around. I think we tend to feel vertical movement. We're a lot more sensitive to vertical movement than we are horizontal movement, obviously. Okay, fun question. Let's stop the video there. We got another one next.